tá certo? Só quero dizer para vocês que a aula magna, ela é o início, como o nosso vice-diretor vai dizer, e ela tem que ser motivacional, né? Ela tem que ser em temas que podem despertar o seu interesse. Nós, físicos, vivemos de motivação. Às vezes a gente tem uma motivação íntima muito grande, mas em 99% dos casos, a gente observando pessoas e a opinião delas, desenvolvemos as nossas motivações e as nossas paixões para levar a ciência adiante, né? Então, a mensagem de uma aula dessa vai muito além da física que vai ser apresentada. Claro que uma das coisas mais modernas é a parte quântica, né? Então ele vai dizer, numa linguagem bem coloquial, os conceitos, as coisas que estão mudando a nossa forma de enxergar o mundo quântico, mas vocês devem enxergar além, tá certo? É o que você pode tirar de mensagem, é o que você pode construir a motivação para essa carreira que nós escolhemos, né? Eu escolhi muito tempo atrás, alguns colegas daqui e agora vocês. E acredite, a gente é movido por aquilo que está dentro da gente. Nós temos que toda hora criar um monumento dentro e a gente vai então lapidando esse monumento. E a motivação é fundamental. Então é por isso que a gente fez o esforço de trazer um físico que é um expert em motivar as pessoas pelo número de pessoas que ele já colocou em física. Tá certo? Então a gente vai começar, peço desculpa, em nome da direção do Instituto, da tradução, mas essas coisas, como sempre, está totalmente fora do que a gente pode controlar. Eu vou chamar o professor Richard Garrett, que é o nosso vice-diretor, para dar início às atividades.
Obrigado, Vanderlei. Bom dia a todos. Meu nome é Richard, para quem não me conhece, que deve ser a grande maioria aqui, com certeza. Mas é muito bom ver o auditório tão cheio para, então, assistir à aula magna do ano acadêmico 2017. Como o Vanderlei falou um pouquinho agora há pouco sobre a importância da aula magna, basicamente representa o início das atividades acadêmicas do ano. E, por isso, a gente busca trazer sempre alguém que, de fato, vai motivar vocês, vai contagiar vocês com seu próprio entusiasmo pela ciência que desenvolve. E, evidentemente, esse ano não é uma exceção em relação a isso. É um grande prazer, é uma honra para nós recebermos de volta ao IFSC o professor Daniel Kleppner, do MIT, Massachusetts Institute of Technology, que já esteve aqui conosco uma meia dúzia de vezes ao longo dos últimos 30 anos. E eu tenho certeza que no final da palestra dele, vocês vão estar totalmente convencidos de que vocês tomaram a decisão certa de optar por física, vindo aqui, juntando-se a nós nesse empreendimento mundial, que é aquilo que cientistas fazem, que é desvendar os mistérios da natureza e do universo. Não tem nada melhor para você fazer ao longo das poucas décadas que cada um de nós tem na face do planeta. Com certeza, a palestra do professor Kleppner vai servir para convencer vocês que vocês estão no caminho certo. Mas agora eu vou mudar de língua e agradecer a presença do professor Kleppner em inglês. So, I always get a little bit nervous when I have to speak English, because people expect me to do it well. That is not always the case. Anyway, I would just like to spend a few words saying thank you once again to Professor Kleppner. I know you've had a tough journey to get here and only a few hours sleep last night. We really do appreciate your presence with us. We're absolutely certain that your talk will be a stimulating talk, which will motivate our students in there, and they will remember it probably for the rest of their careers. Actually, it's not just a question of welcoming Professor Kleppner to IFSC. I would say we're welcoming you back because in a sense you are one of us. Probably most of you don't know this, but Professor Kleppner is one of only 2 honorary professors of the Institute of Physics here in São Carlos. So in a sense, you're one of us, and we're welcoming you back home. Nobody more appropriate to give the Aula Magna, the inaugural lecture for 2017. Vanderlei, did you want to say something more about Professor Kleppner's scientific career before we actually finally allow him to say something?
Okay. Thank you, Richard. Richard is afraid to speak English. I am always in panic because I know that I'm going to do some mistakes. But I will just introduce you Professor Daniel Kleppner. And for me, it's hard to introduce Dan Kleppner because I've been speaking about him my whole life. He is a mentor. He was a mentor for me and for other people in Brazil. I think Brazilian students doing physics at MIT met Dan Kleppner and got the enthusiasm that he can pass to us. And so I've been speaking so long about Dan Kleppner that I don't know if I can now say in a compact way 5 minutes of his career. Dan Kleppner is an American. I think he did his high school in New York.
Near New York.
New York. And already in high school, he got some very important mentors that was telling him indirectly that his talent was physics. I don't know if you believe at that time that your talent was physics. It seems that you didn't know exactly in high school to take the decision. But some people in his life, in high school, were fundamental for him to take that decision. They give him the right motivation. And then he decided to study physics. And at that time, physics had a lot of different challenges. But he was motivated enough and moved to England for his bachelor. And got his bachelor degree. And doing his bachelor degree, he also met people that was mentor to him, that drive him to the right direction. And I learned from him that you hear about Norman Ramsey when you didn't know him yet. And you read his book about nuclear momentum.
Mm-hmm.
And then his professors in the undergraduate told him, oh, that's a field to go. It's called atomic physics. And then after finishing, he decided to do his PhD. And then is when he landed at Harvard University. And surprisingly, walking in the corridor, he found the name of Norman Ramsey. And I said, this is the guy. And then he started to study his PhD with Norman Ramsey. That's Nobel Prize in 89 in physics. And one of the key persons for atomic clocks and hydrogen maser and everything. He did a thesis, and he basically invented the hydrogen maser that today is a very important device in all the telecommunication, navigation, and so on. After finishing his PhD, he decided to continue on this. And he was hired as assistant professor in Harvard first, and then a full professor at MIT. And at MIT, Dan Kleppner did work in fields that today are very fundamental for us to continue to understand the quantum nature of matter. So he started the field of, he was one of the pioneers at least, in Heidelberg atoms. Heidelberg atoms are atoms very high excited, that tell us a lot of things about how things are going on in between electrons very close to the nuclei and very far. And he studied, I think, the first time, the establishment of a chaotic type of effect in the levels of the quantum system. He also was the starting person for quantum atoms in cavity, quantum electrodynamics. And ended by Serge Roche taking that and getting Nobel Prize 2 years ago. And I think Serge Roche was working with you for a while, right? And Serge Roche came here 2 years ago too with you. But that's not enough. Then Kleppner also works in field of precision. You see, we don't, when we learn in school the fundamental constants, we learn, oh, velocity of light is now definition. Sometimes we forget how much science is behind the determination of fundamental constants. In fact, it's not to exaggerate to say that to determine the precision of nature is the main source of evolution of our knowledge in physics today. Trying to measure well things is what made physics evolve the way it has been done. And then is being one of the seminal person in this field, right? He's, I would say, one of the men behind the atomic clock. But that's not enough. He also worked in the beginning of the quantum gases. We all learn quantum mechanics, and we say, why we don't see that by eyes? In some situation, we do, which is many different effects. One of them is the called Bose-Einstein Condensation. And then Kleppner was one of the brave scientists that say, I want to do Bose condensation in hydrogen. And he started to produce people. Some of the people he produced in his lab did the condensation before he did. At Cornell, Wolfgang Ketterle, Andy Hewlett. At Cornell, and Andy Hewlett got Nobel Prize. And Carl Wyman was also in your lab and also got Nobel Prize. David Weiland is also related to you through Norman Ramsey and also got Nobel Prize. So Dan has touched so important fields that today people appreciate so much that he got all the prizes that a physicist can get. I'm not going to read all the medals, but this year, 3 weeks ago, about a month ago, was in January, the APS, he got the most important prize in the United States, which is a prize they give for recognition of the overall work you have done in physics. So he's one of those recipients. He did not get Nobel Prize yet. But he tells us that doesn't matter. And really doesn't matter because he didn't get one Nobel Prize. He got 6. 6 of his students or people that passed to his lab or is related to him got Nobel Prize. I think you then walk to the Nobel ceremony more than any Nobel Prize that we know. And of course, he is one of the legend of MIT in physics. He started many important fields. He worked with people that, if you see the names, there are people that even today we study the books. And so we thought it was a great idea to bring Dan to tell you a little bit about the history of all this and what still left behind for us to do, which is some of the things you have to learn. There is one important thing with Dan Kleppner. He believes that you have to have mentors. You have to watch people. You have to get example in science. And you know, Dan, you've been my example for many years and always accepting invitations and always receiving us, not only me, but many Brazilians that go to MIT. And we appreciate very much you here. And please, you have the time now to give your lecture. Thank you.
Okay. Yeah. All right. I will try to use this, but sometimes I get excited. Anyway, what I wanted to say is that over these years, I've watched the university develop, and that's been a great pleasure, because now there is such wonderful physics being done here that it is always a joy to visit. I also enjoy visiting because people here are so friendly, and the food is so good that I always think of Brazil very warmly, and of this institution very warmly, and Vandelay very warmly. He's an institution in himself. Vandelay told you a little bit about my career and the importance of mentors, good teachers, and they've been very important to me. My high school teacher was Arthur B. Hussey. He taught me in my senior year. That's the first time I really encountered physics, and he was so inspiring. I left knowing that I wanted to be a physicist. That's very helpful if you know what you want to do at an early age. Along the way, I had sort of other ideas when I learned about other things, but it's always been physics. In my college, a little college in Massachusetts called Williams College, a liberal arts school, they had a very fine physics department, and the teachers there were very kind to me. I wanted to do a project on my own, and they gave me laboratory space and spent a lot of time explaining electronics to me. So I had a good deal of experimental experience as an undergraduate. Then I went to Cambridge University for 2 years as an undergraduate. And in my second year, I had a very wonderful young physicist, Kenneth Smith, who told me about the work that he was doing. And I think that's a good place to leap off into what I'm really going to talk about now. I'm going to talk, it's basically about my research. And this is kind of distorted because there are so many things have been going on during that period, so many wonderful advances. So I'm just talking about a few of them. And so many people collaborated with me and worked with me that I can't start to list them all. So please don't get the impression here that I'm the man who did everything. I'm the man who directed the students who did everything. Now, this field, which I've called quantum science, is basically the science which has emerged since the discovery of atom cooling and cavity QED. These first emerged about 30 years ago. They started to develop, and the field has exploded now. It is, well, the best example of that explosion was this award the American Physical Society gave me this year. This award was selected by representatives of all of the divisions of the American Physical Society. And what it does is to recognize that this field itself is now a forefront field and one of the most exciting fields in physics. Last year it was given for the first time in theory for the creation of string theory by Ed Witten. This year they gave it for the creation of what I'm calling quantum science here, for this body of work which has stimulated so many people and has caused such excitement. And I would like to show where some of that came from. Now, I know that most of you here are just starting out in physics, and you may be wondering how you ever get to where physics is really done. It seems so remote, so far away. How does one do physics? Well, I'll give you a few examples of how these ideas grew and how important it is to talk to others, to interact with others, and to keep your eyes open and to have the right combination of courage and foolishness. So, the first seed. By a seed, I mean some idea which has grown and propagated, and this is atomic clocks. And I want to go back to the beginning since most of you do not know that much about modern physics. So it begins with a famous experiment done in 1922 by Otto Stern and Walter Gerlach at the University of Hamburg. Stern was pioneering a subject called molecular beams. This is physics you do by letting a stream of atoms go through a high vacuum so they can move without deflection. And what he was doing was studying the properties of atoms which had little magnetism to them. The electrons going around basically form a little magnet. And because of that magnet, if you put them in a magnetic field, the magnets, they try to align along the field, but because of their angular momentum, it's just like a gyroscope which precesses around. If you put it in a non-uniform field, they feel the force. And what he did was to take, there is the laser pointer, there's a yes. Yeah, thank you. No, I can do it easily. Yeah. No, it's okay. Here's a stream of atoms going through a high vacuum, and they're going through this magnet, but the magnet, as you notice, it has one sharp pole and one rounded pole, so the field is a very non-uniform field, and that causes a force on the atoms. So they start moving up or down, depending on how they are oriented with respect to the field. Now, according to the laws of classical physics, they could be oriented anyway. What Stern found is that the atoms which came out, which he measured, deposited on a screen, some got deflected up and others got deflected down. There were none in the middle. They weren't oriented anywhere. And in fact, this was proof of what's called space quantization. The angular momentum could either point up or point down. This was terribly important in propelling the creation of quantum mechanics at the time. An American who went there a few years later, I. Robbie, told me that people were just amazed. They were coming around for the first time. They had to take quantum ideas seriously. So this experiment launched the golden age of quantum mechanics, which followed very quickly with the works of Heisenberg and Schrödinger and others. Now, yes, there's Stern. He received the Nobel Prize in 1943. It's interesting, Einstein and Stern were friends, and Einstein took an interest in Stern's work and sort of advised and collaborated with him. Now, this young American physicist who was there, I. Robbie, returned to the United States and continued working with this deflection of molecular beams. He set up a laboratory at Columbia, and yes, there he is. He received the Nobel Prize in 1944. He was using this deflection method. This is a Stern-Gerlach magnet there and another one there, pointing in opposite directions and deflecting the atoms first one way and then another. What could you do with this? Well, by looking at these deflections, you could find out about the nuclear properties for the atoms. He was really interested in nuclear physics, and he was measuring what are called nuclear magnetic moments by looking at the deflections of atoms and fields. And then he got, in 1937, a fantastic idea. What he did, what he did was to put another magnet between the two deflecting magnets. It's called the C magnet. Oops. And in that C magnet, he put on a radio frequency field. Now, I told you that these atoms precess around the magnetic field just like little gyroscopes. Well, it turns out if you put on a rotating magnetic field, which precesses the same way, you can reorient the atoms. You can go from one state to another. And when you do that, you detect it because they don't come out the other end. If they change their state here, they'll be deflected one way there, but the wrong way over there, and they'll miss the detector. And that's the principle of microwave nuclear magnetic resonance. So this had fantastic consequences. What I've shown here is you may recognize it. It's a resonance curve. It's what happens when you take a harmonic oscillator and drive it. The width of that curve depends how long the atoms in the oscillating field, how long you spend to take the measurement. If you keep the atoms in an oscillating field very long time, it gets to be very, very narrow. If it's a short time, it's very broad. The frequency with which this occurs depends on the strength of the magnetic moment of the atom and the magnetic field. So using this method, you can start measuring magnetic moments with very great precision. And that is the basis of the atomic clock. In the atomic clock, you're not measuring the magnetic moment, but you are measuring a transition frequency in the atom, which reorients the electron. And this had a very interesting consequence just then. Robbie, conceived the idea that you could use this technique to make a very carefully tuned oscillator, which could be used as the basis of a clock. So here is an article by William Lawrence in the New York Times in 1946, Cosmic Pendulum for Clock Planned. It reports Robbie's proposal. This is an interesting proposal because this is the only written report on it. Robbie never published a paper on it. He just gave a speech. He didn't really like writing, which is a fault. But there was a very good reporter, and he reported that. And one of the things that's in the article, Professor Robbie said that he would like to see someone build an atomic clock that would be capable of providing, for the first time, a terrestrial check on Einstein's postulate that the gravitational field produces a change in the frequency of radiation. Well, Kenneth Smith was doing molecular beam magnetic resonance, told me about that. I met with him. We had the tutorial system at Cambridge, and he was my tutor. And I remember him telling me about that. And the idea seemed absolutely fascinating. That gravity could affect time seemed to me inconceivable. Well, it was inconceivable to me at the time, although now I can conceive of it because it's true. But I didn't do anything about it. I was still an undergraduate. Should we try that? All right, we'll try a better mic. Anyway, I remember that idea stuck in my head. After Cambridge, I went to Harvard University, and I met Norman Ramsey. And that was a very fortunate thing for me because he was a great physicist, a great mentor, turned out to be a lifelong friend. But I walked in at a good time because he just had a great idea. Let me go back a bit, though, because Ramsey invented this method called separated oscillatory fields. And this is the method which allowed Robbie's idea of an atomic clock to become a reality. I'll explain a little bit about what it means. What it means is, I said that the longer the atoms spend in that interacting with the radio frequency field, essentially the longer the time you're making the measurement, the sharper it would be. And Ramsey wanted to make a machine longer and longer and longer. The transitions he was looking at depended on the strength of the field. And one of the problems he had to encounter was that as you made the precision higher and higher, you had to keep the field more and more uniform, and that became a terrible problem. And then he realized that if the atoms are going through a long apparatus like that, where you're making the measurement, and if instead of having this oscillating field on the whole time, you just have it on here and there, you'll get an interference pattern, you'll get a resonance pattern, which has what he thought was two very nice properties. One was that the frequency didn't really depend on what the magnetic field did in here. It was just the average field which came into it. And the other one, to his delight, is he found that it was inherently a little bit more precise than the Rabi method. What I'm showing here is a comparison of resonance curves. This is the normal resonance curve with Rabi resonance. If you have the same length overall, you get a somewhat sharper curve there. So we thought that was very exciting, immediately put it to use in his lab. And then it only became apparent later how really important it is, because it's the basis of, I can't say most atomic physics today, but much of it. For instance, we use a different language right now. Instead of just talking about the quantum solution, we think of the system as an interferometer. You have an atom coming in one state here. Over here, you put it into a mixture of states. And over there, you unmix the states, if you like. You get an interference pattern between here and there. So that's just a different language. But what's very interesting is in between, you don't know which state the atoms are in. They're in what we call entangled states. This is this very weird quantum property where a system can be doing two things at once. And this idea of entanglement is now crucially important to the subject of quantum information theory, quantum measurements, and is a mainstream theory. So here's an example of how a new idea suddenly takes on new meaning, that you may not know what the idea is really good for at first, but if it is really new, it's likely to have unfold riches. And that's true of atomic clocks also. This is a picture of Ramsey. He got the Nobel Prize for this in 1989. In 1954, his method was used to make an atomic frequency standard using the cesium atom by two scientists at the National Physical Laboratory in England, Essen and Perry. This is an atomic beams machine, and you can, where these two arrows show the two separated fields entering the apparatus. So this launched the creation of atomic clocks as a modern technology. It developed very quickly. In 1956, Zacharias at MIT and some others decided to take this laboratory clock and make it into a useful clock. It's a laboratory frequency standard, if you like. Turn it into a real atomic clock. It took a lot of fancy engineering, but this is the first real atomic clock. Huge cabinet, very complicated, but it worked. And it launched the modern atomic clocks of today. These clocks, the cesium beam atomic clocks, until recently were the world standards. And in fact, they still are, in a way, the world standards. But they improved by a factor of 10 in accuracy every decade. Now, that was 1956. We are now 60 years later. That would be 6 factors of 10. The first clocks were roughly 10 to the 16th, 10 to the 10th accurate. The ones today are about 10 to the 16th. So that has been a very nice chapter. But what has come out of the atomic clocks is something nobody dreamed about. What's come out of the atomic clocks are the global positioning system. Now, the global positioning system just is incredibly important. It's a great boon to mankind for many, many reasons, in addition to being able to drive around town more easily. Turns out if everyone can drive around town more easily, nobody can drive around town more easily, but it's still very nice to know where you're going to go. If one were to go to Congress to try to explain why it's important to do basic research, you can't think of a better example than this. If you went to Congress and say, I want money to study Einstein's theory of general relativity. Well, Einstein's theory of general relativity is about the least practical theory you can ever think of. And I might say when we were, the motivation for these clocks, as I'm shown from Robbie's talk, from my own experience, and also from Ramsey, was to measure this gravitational redshift. It was purely basic research, but what's come out of it is this fantastic new technology and new industry. Well, going on to my own work with Ramsey, let me just mention that in 1954, Townes really invented the maser. The maser is another type of device for doing microwave resonance on atoms and molecules. In the maser, you take a stream of atoms, you select them in one state, and you let them go into a resonant cavity. And if some of them start radiating, then the field in the cavity builds up and the others will too, and it's an oscillator. The atomic clocks I've been explaining are passive devices. You have to apply a signal. The reason I'm showing this is a page and a half in the Physical Review, and this is a picture right here. There's a source of maser. This is of atoms or molecules. This is a state selector, and here's just a cavity, and here's a signal coming out. They explain the principle of the maser, the theory of the maser, the construction of a maser, and they give experimental results, and that's all in 1.5 pages in the Physical Review. And I like to quote this as an example that if you write clearly, you can write briefly and say an awful lot. Anyway, this is a maser that Norman Ramsey proposed. It works on the hydrogen atom. It's the same idea. You have a source of atoms over here. You choose atoms in just the state that you want. They go into a microwave cavity, but they don't fly right through it. They go in and they bounce around and they spend a lot of time there, maybe a second instead of a millisecond. This means this thing would be 1,000 times more accurate than otherwise. And this is his proposal for making a hydrogen maser. And that he was just thinking about that when I came along, so I started working with him. I did an experiment just to see whether atoms can bounce at all and still maintain their state coherence. Turns out they could, and with that knowledge, we went on and built the hydrogen maser. And the hydrogen maser has turned out to be a very useful device. Yeah, this is a picture from the original publication of it, but it shows just the same thing. I mean, the important thing about it is the simplicity. Source, state selector, cavity, and a storage bulb. And there's what it looked like. The most conspicuous thing here, these large disks are just big Helmholtz coils to cancel the Earth's field. And this is Norman Ramsey. This is myself. This was myself. And this was my student, Stuart Crampton. So the maser turned out to be surprisingly useful because of its simplicity. You don't need to make a very good oscillator. It oscillates for you. It turns out not to be good as a primary frequency standard, and the reason is the interactions of the atoms with the surfaces make the frequency a little bit predictable. Now, in the last 50 years, I've said we have had fantastic advances in clock technology, and in recent years, we've gone beyond the microwave frequencies for clocks to optical frequencies for clocks. I like to show this because this was from Ted Hensch's Nobel Prize lecture in 2005. Ted Hensch really invented modern laser spectroscopy. He was the first person to make it useful, and he is just an absolute genius at developing high-precision methods. And what he got the Nobel Prize for was developing a method which allowed you to do these experiments not at microwave frequencies, but at optical frequencies. And he predicted in 2005, he was extrapolating the precision of hydrogen, but that was really the precision of clocks. And if we continue this thing right down over to there, you're at about a part in 10 to the 19th, which has recently been demonstrated. Now, others contributed to the development of the clocks. Towns for the maser, Castlier, they separated oscillatory field method, Wolfgang Paul, the ion trap in 1989. So all of these people have played major roles in that creation. And now we have what we call this next generation that's gone beyond 10 to the 16th, is currently in the 10 to the 18th region, actually. And Junyi thinks one can go even much further than that. And what contributed to that was laser cooling, the optical frequency comb by Ted Hensch and John Hall, and other quantum control techniques by David Wineland. Now, in a sense, the hydrogen maser is now obsolete. It can't reach those precisions, but it's still very useful. If you go into any primary frequency laboratory where they have machines around, atomic beams machines, there's usually a maser or two sitting over in the corner. And the reason is it's so reliable. They're invaluable for making sure everything is working and keeping running. And if you go to any laboratory involved in very long baseline radio interferometry, this is the technique in which essentially you can turn the whole Earth into a giant radio telescope with fabulous precision. That works because each of these laboratories has a hydrogen maser as a local reference, and then they bring the signals together. So this amazing form of radio frequency spectroscopy in space has taught us a lot about the universe, which we never knew before. We have the highest resolution images of the distribution of hydrogen in space from that. We weren't thinking about that at all, of course, much like the GPS, but those are the kind of things which come out when you have a new technology. Well, okay, yeah. First of all, we not only know about Einstein's prediction, it's essential that you take it into consideration in designing the GPS system. If you neglected it, you'd be in serious error. Fantastically precise checks on whether the fundamental comments are changing. A revolution in spectroscopy and the precision of spectroscopy. And in astronomy, very long baseline. So this suggestion of Robbie that maybe you could use this method to make an atomic clock, you see, has had fantastic consequences. This is what one can expect when you have a new direction in physics. And this is why it's so exciting to be working in physics. Even if you can't think of anything useful that'll come out of what you do, just the new knowledge is bound to pay off one way or another. And in some cases, it really pays off tremendously. Well, Rydberg atoms and cavity QED. This is Ed Purcell. Some of you may be using his textbook in E&M, which is a classic book. He was a professor at Harvard, a wonderful person. Someone said, whenever you talk to Ed Purcell, you go away feeling better, because he had such a nice way of understanding things and clarifying things. And I was still at Harvard at the time, and he told me about something very interesting, namely that Rydberg atoms had been seen in space. Now, these are energy levels of hydrogen. This is the Bohr atom, if you know it. You have the ground state, n equals 2, 3, 4, up to any infinity where the electron and proton are no longer joined. Optical transitions involve transitions between these lower lying states. From 3 to 2 is the Balmer series. From 2 to the ground state is the Lyman series. But if you go from, say, 101 to 100, that transition lies in the microwave regime. It's a few centimeters in radiation. And what a radio astronomer detected was radiation on those transitions. Where they came from were from stars, the atmospheres of stars, which were sort of in formation, and the electrons and protons circulating in space would capture each other, and then they'd bounce down from one level to another. That was called recombination radiation. Yep. And this is a picture of one of the very first spectra. I love that picture because it is so beautiful. It's so clear. It's very hard to get a spectrum that good in the laboratory. This is the line from the 110th to the 109th transition there. This is the same line, but not from hydrogen, but from helium. From this, you can see roughly the fraction of helium in space compared to hydrogen. And these are all other heavier elements there. So Ed started talking with me. We discussed the extraordinary property of these atoms in these huge orbits. Because the principal quantum number was very, very high, the orbits were huge. The size of the orbit goes as the square of the quantum number. So that would be 10,000 times higher and bigger than a normal atom. And if you start looking at the properties of these atoms, they're all very totally bizarre. And that was very interesting. But you could only make these in space. Well, you couldn't make them. You could observe them in space. There was no way to make them in the laboratory. So that's one of the things I had in the back of my head. I think other people must have been thinking along the same lines. But in 1975, by that point, Ted Hench had invented laser spectroscopy. We had lasers to use in the laboratory, practical devices, which allowed you to put atoms in states and manipulate them. And laser spectroscopy was developed by, it's due to the laser by Towns, but it was Arthur Shallow and Ted Hench at Stanford University who really started making lasers which were practical and laboratory devices. So here is an apparatus for making Rydberg atoms. You have an atomic beam, a little oven here, and the atoms go flying through there. We were doing this with lithium atoms, which are alkali atoms. But a Rydberg atom doesn't really care what the atom is as long as one is the electron is very, very far away. And it's very easy to detect these atoms. That's what made the field so powerful. Because with these big atoms, just a small electric field would ionize them. And it's easy to detect ions. So you have a little electron detector over there. And here is what the energy levels of hydrogen look like in an electric field. This is lithium. These all look very regular, except you see there's a little gap over there. Well, that's because lithium isn't exactly like hydrogen. But this is sort of a map of the energy levels. And here is a form of spectroscopy. What we're doing is sweeping the laser at that electric field and that electric field, and then plotting all the spectra like that. And you can see, you can match them up right on with the energy levels. So it's a very nice way of looking at rather complex atoms. Here are the energy levels of a hydrogen atom in a magnetic field. Well, actually, this is lithium. But these are starting to look rather complicated. And we got very interested in this problem because one thinks that all problems with hydrogen atom can be solved. It turns out this is a very difficult problem to solve. The problem is, what is the motion of an electron around a proton in the presence of a magnetic field, say, like that? And we became very interested in trying to understand that. We tried to understand this as a problem in quantum mechanics because that's the language we like to think in. Well, it turns out that if you look up here, and if you look at the classical motion of the system, the classical motion becomes chaotic. You know, chaotic motion is motion in which the smallest change in initial conditions produces huge changes in the motion in a while. It's a very fascinating subject, chaos is, but the question of the connections between chaos and quantum mechanics is even more fascinating because quantum mechanics doesn't appear to leave any room for chaos. That quantum motions eventually are all periodic repeat. Chaotic motions never repeat. So we became very interested in that, and we worked on that problem for some years, and others worked on them too. But another thing one could do with cavity QED was to pursue another idea that I'd really gotten originally from Purcell. Purcell pointed out in nuclear magnetic resonance that if you look at the lifetime for spontaneous emission of atoms in say, nuclei in a magnetic field, the lifetimes for going from, if they're in an upper state, to go to the lower state, this is a process called spontaneous emission. And all atoms, all quantum systems, will eventually go down to their ground state by emitting the energy through some emission process. That's called spontaneous emission. And you normally neglect it at the long frequencies of, the long wavelengths of magnetic resonance experiments. But Purcell pointed out that if you put these atoms in a good resonator, in a high Q cavity, the spontaneous rate is increased. That was just sort of a side comment, an interesting observation that physicists publish. It had very little practical consequence at the time, but once we could start making these Rydberg atoms, I just wondered whether one might be able to see this effect. In fact, what I was looking for was the opposite effect. At the time, there was a great interest in measuring what's called the Lamb shift in hydrogen better. It's a fundamental test of QED. And so I actually proposed this idea. I didn't publish it. Maybe I was too chicken because the idea seemed too wild. But the Lamb shift is in hydrogen, if you look at the ground state, the 1s, the 2s state, and the 2p state, by the simple Dirac theory, should be exactly the same. That was the best theory of atomic structure at the time. It was known that the 2s state is actually, its energy is increased. It's no longer degenerate with this 2p state over here, but it's pushed up. That was discovered by Willis Lamb in 1948. He received the Nobel Prize for that. And it was a key test of relativistic quantum electrodynamics. And the problem was it was very difficult to measure the Lamb shift with very high accuracy. And the reason for that is you're measuring the difference between the 2s state and the 2p state. Now, the 2s state is what's called a metastable state. Its spontaneous emission rate is it takes about a second. But the 2p state radiates in a small fraction of a microsecond. So you don't have much time to make the measurement. And I speculated that if you were to put this atom in a tuned cavity, but it was not tuned to the wavelength, but to some other wavelength, the atom wouldn't radiate. that was called inhibited spontaneous emission. It was just an idea. But I realized that once we had the Rydberg atoms, we could try it out. So one of my students, Randy Hewlett, did this with me. The idea is you have two disks over here. These disks are separated by less than half a wavelength of the radiation that would come, and they wouldn't be able to radiate between the disks. So in the experiment, you sent atoms through the disks. Instead of varying the distance of the disks, you could change the wavelength by changing the electric field. And here's what we see. Atoms come through, but most of these atoms, many of them had decayed before they got to the other side. When you get to this cutoff region where they can no longer radiate, the lifetime goes way up. So it's a rather crude demonstration, but it does demonstrate what's called inhibited spontaneous emission. And that generated a lot of interest in the interactions of atoms with a vacuum, with the radiation field. Well, it turns out a lot of phenomena followed from that. For one thing, the reverse can take place. You can use the Purcell effect and enhance the rate. You can get the atom in the cavity to oscillate back and forth. You can get the atom in the cavity to oscillate back and forth when there is initially no photon in the cavity. Just put an excited atom in the cavity, it radiates, and then it absorbs again, and you have what are called vacuum-Rabi oscillations. The field is really just burgeoned. Much of the things that I mentioned, for instance, on quantum information theory and quantum control, have come from this cavity QED. And Serge Haroche got the Nobel Prize for that in 2013. The experiments are truly extraordinary. He can make a quantum entanglement between an atom and a cavity. So they're one quantum system. You can't really think about them as separate systems anymore. And in fact, you can entangle two atoms in a cavity, but if it's the same cavity, then the two atoms are entangled with each other. So it's a whole new world. Okay. Well, let's see. Let me talk on the Bose-Einstein condensation, where that came from. Well, it came from a letter in the Physical Review Letters by Stwally and Nosenow, pointing out that if you have hydrogen atoms which are all pointing in the same direction, it's spin polarized, that they can't form molecules. And they will stay atomic even down to the temperature of absolute zero. And if that's the case, you might be able to get them into a temperature regime where you see this phenomenon called Bose-Einstein condensation. Now, I saw their article and put in some calculations, and I thought the proposal was totally absurd because the conditions were just unlike anything which had ever been achieved. My colleague, Tom Graytak, asked me about the article, and I explained that. And he said, well, that's too bad, because Bose-Einstein condensation is really very interesting. And I said, what is it? And he explained to me what it was. And so we set to work trying to figure out if there's some way to do it with hydrogen. Now, at the time, this is the only atom that you could conceive of for doing these experiments. And I made use of information that I had had from making the hydrogen maser to propose some new techniques for doing this. So we went to work on that. One of my students who just gotten this PhD but hung around because it sounded interesting to him was Bill Phillips. Well, Bill Phillips was one of the inventors of laser cooling, for which he got the Nobel Prize. And it turns out that the laser cooling method was much better for getting Bose-Einstein condensation. Nonetheless, interest in the field kind of developed. We were interested enough to go to work on it, and other groups also went to work on it. So I mean, this is a quick picture. This is the potential between two hydrogen atoms. If the spins are parallel, they repel. If they're anti-parallel, you can form a molecule. That's the basic idea. And we need high density, low temperatures. It was very vastly different from anything which had been done before. But we thought the prospects looked very good. And in fact, as we started out the experiments, everything looked just terrific. We started really publishing results in 1980. Here are three groups which were seriously, and then other groups joined in. Our method was very simple. In a magnetic field, the hydrogen atom has four possible energy levels depending on the spin of the electron and the spin of the proton. And if you want to work with these atoms over here, if you let them flow into a very strong magnetic field, the energy goes way down. They get accelerated as they come in, they thermalize the walls, and they stay trapped. Very simple. And we made an apparatus to do that. Again, this was in principle a pretty simple apparatus. You just let hydrogen flow in, you measure the pressure, and you turn on the discharge, and the pressure goes up and up and up. Those were in our first experiments. And of course, we wanted it to go up to basically to infinity. But things don't go up to infinity, because just over here, it starts rounding off. You're losing the atoms some way or other. We spent a long time trying to figure out just how they're lost. And it turns out they're eventually lost by three-body recombination. So our method, we needed a totally new method. The problem in our method was that the walls of the cell were causing the trouble. We had to confine the atoms without a cell. Well, oh yeah, we did some experiments where we actually tried to very quickly compress the atoms and measure what went on as you may go to very high density very, very quickly. But we were stuck. And then we had a very good postdoc, Harold Hess, and he suggested that instead of working with these atoms, we work with those atoms over there. You could trap them in space. You can't have a magnetic field maximum in space, but you can have a minimum. So you can make it a trap for those, but you have to get the atoms into the trap, and you have to be able to see them. So this is the type of trap that's used. It's called a Yaffi Pritchard trap. Along the axis of the trap, there's a very small magnetic field. These coils give you a larger field at each end, and there's a minimum in the center. And the idea is that you can get the atoms in the trap and then lower one end of the trap, that the fast atoms would escape and the other atoms would cool. It's evaporation. And this process of evaporative cooling was proposed by Harold Hess. So we went to work. We made a system which would do that. It was kind of interesting to detect the atoms. We actually made what turned out to be a low-temperature hydrogen maser. This thing would oscillate if the atoms in the trap are kept for a while and left out. Just at this time, laser cooling was being invented. My students were heavily involved with that. What they did was terribly important. You're always very proud if your students do very good work. But sometimes the work can be too good, because it turns out that laser cooling is infinitely better than our method, although the laser cooling experiments also use evaporative cooling, so we did make a contribution to that. Well, time is getting on. I would just summarize rather quickly. It's very difficult to see hydrogen atoms. Spectroscopy of hydrogen is very difficult because the wavelengths aren't available with lasers and the radiation is difficult to treat. It took us a long time. The method we used for looking at atoms in the trap was to excite this 1s, 2s transition. The atom absorbs 2 photons to get over there. And 2 photon transitions require a lot of power, and a lot of power is difficult to provide there. And then when they're there, we put on a little electric field that mixes the 2p state and the decay. And this is a Lyman alpha photon, and that's what we detected. So the apparatus looks like this. Here are the Yaffi Pritchard coils. Here is our laser beam going through there, and here is a detector at the bottom. The experiment was very frustrating because these very low temperature experiments in cryostats at sub-millikelvin temperatures are just inherently very difficult. If you need to adjust anything, you have at least a 1 month and typically 3 or 4 month cycle time. So we worked away on it. We completed the laser system in '91, and for 4 years we couldn't get a signal out of the apparatus. The students were wonderful because they just would not get discouraged, and they kept trying. And eventually we got a signal. But before we did, Bose-Einstein condensation was discovered at Gila and then at MIT by Wolfgang Ketterle. So we were not going to be the first to discover Bose-Einstein condensation, and one always likes to be first. But we did get there. We got an inkling of a signal in '95. This doesn't look like a great signal to you, but we could recognize it as real. And there's a wonderful aphorism in physics by John Hall: you can't tweak up zero. If there's no signal, you don't know what to do. If you have even the smallest signal, you can start improving it. And we did. Over a couple of years, it got bigger and bigger. We used a method called radio frequency evaporation. We have the atoms kept in a trap over here, and by applying a radio frequency field, we could let them escape at different energies. And then in 1988, we actually discovered it. Without going into all the details, I can say these red points over here are Bose-Einstein condensed hydrogen. So we finally achieved what we set out to achieve. And when I reported that at the Vienna conference that July, I got a standing ovation, which moved me deeply. And the reason, well, I think the reason was we'd been working on this for 20 years then. We started the field and hadn't gotten anywhere at all, and people were feeling sorry for us. And then we succeeded, and they were very happy because of that. They were happy for us. And I was very happy for the field itself because it has turned out to be so productive and done so much for physics. So I'd like to end by talking about an incident of mentorship, which is not by me, but by my student, David Pritchard. Dave Pritchard was working on laser cooling in the late 1980s, had very creative ideas. He was one of the leaders in the field, and he invited a postdoc to come to work with him. This is an interesting invitation because the postdoc had no experience in that direction before, but Dave had pretty good instincts and decided this guy is pretty smart. This guy was Wolfgang Ketterle. So he hired Wolfgang as a postdoc. And it was clear that Wolfgang was exceptional, had great ideas, and that he shouldn't continue to be a postdoc for Dave. For one thing, other universities were offering him positions. we wanted to offer him a position at MIT, but the problem at MIT is that we have a long tradition that young assistant professors don't work in collaboration with senior professors on a project for good reason. There's no way to determine who did what. It's called the shadow effect. And so that was a problem. Dave solved the problem by stopping his work completely. He turned over the apparatus to Wolfgang, did other things. He's very inventive and had lots of things going on. He did other things, but he opened the way for Wolfgang to get the Nobel Prize, which Wolfgang got a few years later. And I think this example of opening the way to a younger person, to making the science go forward, to putting their best interests and the best of interests of science ahead of your own is a golden example of mentorship. So I'm very proud to be in a profession where things like that happen. I'm very proud to be in a profession where truth is venerated, because I don't know if you've ever been following recent political developments, but the idea of truth seems to be under attack. And I think that's terribly dangerous. In science, we know truth and we respect it, we look for it. And that's one of the reasons that physics is such a great profession. So I wish you all good luck in your studies of physics. I hope it gives you a lot of pleasure. Whatever you do, physics is wonderful for doing many, many different things. But here are a few examples of some things which grow out of earlier work. Thank you.
We have time for one or two questions. Oh, by the way, in commemoration of Professor Kleppner, Physics Today put together, he's one of the physicists that wrote more articles in Physics Today. General ideas, physics. And there was a special issue. And we brought a few of them. So who put a question, will get a copy signed by Dan Kleppner. So, who wants a journal signed by the author? Or you have to make a question.
My name is Marcela, and first I would like to know if you like to be my grandpa. This is my question.
I didn't.
She wants to know if you would be her grandpapa. Grandfather.
Thank you. I'm very impressed and very inspired. Actually, I'm afraid of changing my major to physics. I study computer science, but it's very interesting. I just would like to know what kind of research is doing today, like in USA and in Brazil, related to the atomic clocks.
Yeah, the research on atomic clocks. Well, it's a terribly interesting frontier that Yunyi at NIST, who currently holds the record in precision of clocks, has got them to a part in 10 to the 19th and thinks you can even do much better than that. But at that level of precision, a very unexpected question arises. I mentioned this gravitational redshift. Clocks at different altitudes, identical clocks will not keep the same time. That's the effect of gravity on time. Now, when I started in this business, we just wanted to see whether the effect was real. Now it's known that it's real, and it's used in the GPS system. You take it into account. But it's now gotten into a point where it's causing what I consider fundamental problems. If you want to compare two clocks, you have to know the difference in gravitational potential, essentially the height between them. That difference comes to about a part in 10 to the 17th per centimeter of that order. If you want to measure the clocks in two different locations, you have to know the difference in gravity at the two locations. You might think you just need to know the difference in altitude, but that isn't correct. The reason is that when we measure height, we measure from a hypothetical surface called the geoid, which is a surface over the Earth where G is constant everywhere. It varies a little bit over the Earth because of land masses and water masses and things like that. It turns out the geoid itself fluctuates around. It fluctuates about typically 4 to 6 centimeters on the time scale of minutes to days, just due to the changes in the Earth, the water distribution on the Earth and the atmosphere. So there is no way to really establish the difference in potential between two clocks. Well, you could say then, well, let's just define the second as measured on a clock, I don't know, say in, I don't know, in San Carlos, yes. This means that if anyone else wants to know whether their second is a good second, they have to come here. That isn't very practical. You'd like to be able to calibrate your clocks anywhere, but you really can't do it. And the reason you can't do it is you can't separate time from gravity, and you can't separate the gravitational field from mass. So suddenly we have time and mass stuck together in a way we hadn't thought about before. And we have to think about it now. And I don't know quite how to think about it, except you can always define the local time if the two clocks are at the same place. But even that's going to break down at some point because you don't know exactly where the atoms are in the clock, and they won't be at the same place. So this, I think, new understanding of gravity and time is one of the things which is going to be coming out of this. And that's very unexpected, but that's one of the nice surprises in physics.
Hi, Professor. It was a very good presentation. My question is, in your slide, you write that the hydrogen is the only atom that is a gas at 0 temperature. I don't understand very well because if we have a gas at 0 temperature, we are talking about a BC, right? How is how it happens?
Hydrogen
Yeah.
is gas, even
Yeah.
at 0 temperature, and you
Oh.
have the right spin state.
Yeah.
But then at 0, you have to have a condensate. So at 0, it's always going to be a condensate.
Well, yeah, if you get it down to low enough temperature, the de Broglie wavelength is large enough, it'll always be what you call a condensate. I mean, the condensate can be a gas, it can be a liquid, too, for that matter. It's the quantum state, the quantum nature of the system, really, rather than just the physical state, which is important. Does that answer your question?
Yeah. But I'm confused because when I lower the hydrogen, I have a liquid, right? Because very, very, very low hydrogen is a superfluid. It's not a gas. If we are talking about a dilute gas, it's another story. But
the Bose condensate is, in a sense, a superfluid state. I mean, this has been beautifully observed. So the condensate itself is a superfluid. It's a gas, but it's a superfluid gas.
Hi, Professor. My name is Rafael, and I don't know if I'm capable to do this question in English.
Fala mais perto do microfone.
Okay. My name is Rafael. Good morning. I don't know if I'm capable to do this question in English, but I'm going to try. What make Bose-Einstein condensation so important. What I mean by that is, what makes that difference from the other state of matter? Why that matter? I mean, what happened to the atom when he is in the state, it is in the state of Bose-Einstein condensation? What makes this difference if an atom is like a gas, in a gas state, or in a liquid state? What happened to him?
The reason is so important is, one, there are real questions about the reality of it. Einstein himself wasn't sure that the concept made sense. Another one, it's an unusual type of phase transition, unique. Normally, phase transitions depend on interactions between particles. You know, they come in, they form into a crystal or a liquid because they're all interacting with each other. The Bose-Einstein condensation is a phase transition, but it does not depend at all on interactions. They can be zero interacting particles. They'll still form that quantum state. So it's a very unusual type of quantum state. The particles which are in the state, if you look at if you take the particle out of the state, if you knock some particle out, it'll just be a hydrogen atom. It'll no longer be in the condensate. You'll have changed its momentum. You know, to look at it, to look at one particle, you have to be able to select it. Well, you can't select one particle, but you can select a particle. You don't know which one it is. And it'll just be the particle. It's no longer in the condensate. So the condensate will have changed. The quantum state will have gone from n to n-1 particles.
First of all, thank you for sharing your story with us, and also for the inspiring lecture. My question is a little bit simpler. I believe it involves less concepts, but you talked about 3 seeds of quantum mechanics and their importance along your career. I would like to know if you could point out any current research field that is promising in terms of the future, something that could lead us to an important advance in quantum mechanics with the same effects, perhaps, as those that you commented today.
Well, the usual answer to that question is, if I knew, I wouldn't tell you. I'd do it myself. But it's hard to speculate on that. Any interesting new physics, which involves phenomena that when people haven't seen before, has the potential of blossoming that way. There's a wonderful saying by a French philosopher, scientist, Teilhard de Chardin. He was commenting really on the development of living beings in the universe, but it's perfect for science. He said, the history of the living world is an elaboration of ever more perfect eyes in a cosmos in which there is always something interesting new to be seen. And as we get better eyes, we will see new things and they'll be interesting. So anywhere you can probe that hasn't been looked at before has that potential. Yeah.
Thank you.
Okay.
Hi, Professor Kleppner. I'm very glad of hearing your motivation and the history of your work. My question is much simpler. I was wondering, how did you spend time during your studies, like during your undergraduate studies and your postgraduate? If you managed to have time for leisure and seeing people, or if you were that kind of student that just spent time at the libraries, and what would you think that that would be important for us.
Are you asking,
So you
have-
had a lot
have
of
I ha-
caipirinhas as a student?
have I had a nice life? When I was an undergraduate, looking back on it now, I did a lot of things. I mentioned that I made up a project of my own that I worked on very hard. I remember going into the little town at 2 or 3 in the morning. There was a midnight diner, and you could get a donut and a cup of coffee for 5 cents. And that was very valuable to keep me going through these long nights. But I wasn't spending all my time on long nights. I was starting to find out more about the world. This is a liberal arts college. I took courses in English literature, which really excited me. And I thought for a while, maybe I should major in English literature because I'd had the rest of my life to do physics. But I stuck with physics. I did, in the summers, well, I liked my college, my teachers very much. I didn't really like the college, so we made a plan to graduate early, a year early, by taking more courses. And this summer I went to Cornell University to summer school there. I remember that because I was trying to understand Ampere's law, and I was really stuck on the concept of a line integral. So I spent my summer learning what a line integral was. But anyway, I did work, and I worked awfully hard to get out of there soon to go to Cambridge University. And Cambridge, well, as I've explained, was very good for me as an undergraduate there. It was very good for me because I got propelled into the graduate work at Harvard. I also met a young lady called Beatrice on the ship going over. She's sitting right there, and we had our 58th anniversary last summer. So that's also how I spent my youth. I like to hike and travel and do things like that. When I was much younger, I had many hobbies, and I still do. I love to do furniture design and woodworking. I like music. I like art. I like good wine. And I like life as a physicist. Now, when I was working at Harvard, that was very intense. I remember being in the laboratory working on building my machine. It was on the 4th of July, and the Lyman lab isn't that far from Cambridge Common, and I could hear the bands playing on the Cambridge Common and fireworks going off, and I was sitting in the office working away, drafting and building, and I was thinking to myself, well, those are just ordinary people. I'm sitting here doing physics. And there was a gem of truth in that. I did work very intensely, and as Beatrice can tell you, in the early years of our marriage, I was in the laboratory much of the time. It's hard work, but anything which is really worthwhile is hard work. So I wouldn't exaggerate the difficulties of physics compared to any other challenging task. The essential thing is you really have to like physics. If you really like physics, everything else follows.
Hi, my name is Carolina, and I'm sorry about the question, but I don't understand very well how is made the isolation of the hydrogen.
I didn't understand the question there.
I don't understand very well how is made the isolation of the hydrogen.
Okay. Hydrogen, in principle, physicists love hydrogen because it's so simple and elegant. In the laboratory, it's really a mean atom. It's difficult to make hydrogen in the first place because hydrogen always comes as a molecule. You can't buy atomic hydrogen. It combines and blows up. So we make the hydrogen atoms in a little radio frequency discharge. You have a tube with a radio frequency coil around it. You give it a pulse, a high pulse of microwave energy. and the atoms dissociate and they flow out. They flow into a vacuum, and the question is, you want to keep them isolated. Well, in the hydrogen maser, you know, we knew that you could bounce atoms off walls okay. In our BEC experiments, the walls were covered with superfluid helium, and atoms bounce off superfluid helium. So once you've made them, they will be stable unless they recombine, and they recombine only at much higher densities. So we have them in there, okay. The real problem of hydrogen isn't so much making it, it's detecting it. For the alkali atoms, for these beautiful experiments on BEC, you've seen these photographs of the gas. You can do that because you can actually take a picture of a gas of atoms, and you don't need that many atoms to get a nice picture. You can't take a picture of hydrogen, and you have to detect it by indirect methods. So that was a good part of the problem, which caused us such long delay. Yeah.
Thank you.
Okay, I know that we have a few more people, so I'm going to invite you to come after all and speak directly with them, because we already have a time, and we know that they have a restaurant that has a time to start and end. So
Okay.
So I want to thank Dan for the nice lecture, and I want to thank you for coming, and I hope that your career will be as brilliant as Dan. We need that in Brazil. But you already see, right? You have to be in love with physics, with many other things, but with physics too. And work hard. Thank you very much, and we still have some journals to distribute.
Good.
Very nice.
Okay. Yeah, thank you.
Some students